So welcome to lecture number 8. So today we will start a new chapter, namely a chapter on Monte Carlo Quadrature. So what is the setup here? So what we are given is a function from Rd to R and an Rd valued random variable x. And our aim is to compute this expectation here, the expectation of f of x, and we call this theta. That's really always a general setup of Monte Carlo Quadrature. And we have already seen a special case, namely the numerical integration on 0, 1D. And in this case, our random variable x is just uniformly distributed on 0, 1D. And in this case, theta is just the integral over 0, 1D fx dx. And of course, for everything to be well defined, f has to be integrable, and also this expectation here needs to exist. Since we already spoke about integration, so here's a small recap, namely example 2.1, where we introduced Monte Carlo integration just by doing the classical Monte Carlo method. What's the classical Monte Carlo method? Well, we have random variables z1, zd, which are IID copies of a random variable which is uniformly distributed on 0, 1D. Well, we have this, we plug this into f, and then we average. And then we already computed that the mean squared error, so here's a square missing, the mean squared error is just the variance of f of z divided by n. So the mean squared error decays with 1 over n, and the constant is the variance here. And we also computed the cost of this method. So the cost is n times c. So c was the cost of the evaluation of f plus n times d. N times d is the cost of all the random numbers we need. So z1 and zn are n random variables, but they are d-dimensional, thus n times d. And then we have plus n, while that's n minus 1 additions and 1 division. So that's the cost. And well, since we have the recap, so here's the recap of the definition of the error. So we need square integrability, and then we define the root mean square error in this way. So it's we compare s of f with our Monte Carlo method. Square takes the expectation and then the root. So it's the root mean squared error. And while on the previous slide you have seen the variance in action, the variance comes into play if our Monte Carlo method is bias-free. That is, if the expectation of our method is already the value we want to compute. So if this quantity here is 0. And then if we have a bias-free method, then the mean squared error is just the variance, because this thing cancels here. And we have always this relation of the mean squared error. The mean squared error is the variance plus the squared bias. And another recap, what's the computational cost, or what's our cost model? So the computational cost of the algorithm is the weighted sum of the operations. And usually is what we are doing here. So input, output, copying and addressing all have cost 0. Arithmetic operations as plus, minus, multiplying and dividing has cost 1, as have comparisons and evaluations of elementary functions like sine, cosine, ceiling, etc. Also our random number generator has cost 1. So one random number costs 1. And well, here we have those cases, so either uniformly on the whole interval from 0 to 1 or uniformly on just 0, 1. And calling the oracle was the most expensive. So calling the oracle, we need to evaluate f, and this has cost c. And this cost c here is much larger than the dimension of the problem. Well, and if we have this model, well, we can define a random variable for our Monte Carlo method, which measures the cost. So because the cost may depend also on random input. And well, then coming from this variable, we just average to get the cost of our method. And well, for Monte Carlo integration, For classical Monte Carlo, well, we don't need to average because this here, the cost of this method is deterministic. It's not a random variable. The method itself is random, but not its cost. Okay, so what is Monte Carlo integration good for really? So if you think of your introduction into numerics lecture, there you have seen methods with order 2, 4, and so on. So why do we need Monte Carlo integration? Because classical Monte Carlo has convergence order 1/2 with respect to the computational cost, and 1/2 is not really high. But all the examples you have seen in your introduction to numerics lecture, they are one-dimensional. So 1/2 sounds only okay, but this is actually quite good for high-dimensional problems. So to formalize this, let's consider this class curly m and that. So n in n is fixed, and n is the number of knots at which we evaluate our function. So the quadrature formulae look like this. So we evaluate f at the knot xk, we multiply with ak, and then we sum. That's the standard quadrature formula, which you have also seen in the one-dimensional case in your introduction into numerics lecture. So now we're considering the whole class here. And then there's a lower bound, which is summarized in this theorem here, which goes back to Bachwalow from 1959. So what do we have here? First, let's look at this curly f of r. So curly f of r is our class of integrands, and here we assume smooth integrands. So f is in CR, and we assume that if you look at all the partial derivatives of order r, then they are uniformly bounded by 1. So alpha I is runs from 1 to d, and I runs from I to r, and this d alpha r, d alpha 2, d alpha 1, these curly d's, that are the partial derivatives. So we are working with a class of smooth integrands, so CR, and have this bounds on the partial derivatives. Okay, and that's the class of the integrands. This is the class of the quadrature formulas. And now the statement is, so for fixed r and d, we can always find a constant such that this worst case error here is greater or equal than CRD times n minus r divided by d. And the worst case error is, so we fix a method, we soup the error over all the problem instance, which are all the functions from the class we consider, and then we take the inf over all quadrature formulas. Or otherwise stated, so for each deterministic quadrature formula, we can find an f in our problem class, such that the error is larger than CRD times n to the power minus RD. So, and because R can be low, D can be high, so if you think of finance applications, there's typically the number 360 for 30 years times 12 months. And there you also have typical low smoothness, so this might be close to 0. And in this setup, Monte Carlo methods are really superior for high dimensional problems, if the dimension is high and the smoothness is limited. And well, in lecture number 3, we had this counting problem where the randomized method was also superior. And it's not an analogy, but the counting problem also is at the core of this proof here. Okay, so we have order 1/2 for Monte Carlo integration. So let's summarize. So this is the thing we want to compute. F needs to be square integrable. Classical MC is given by this. Z1 up to Zn are IID copies of uniformly on 0, 1 distributed random variables. We plug them into F and average, and then, well, the mean squared error is given by the variance divided by n. So if we take the square root, we have here the square root of n, and so order 1/2. And the cost we have already seen for classical Monte Carlo is proportional to n, and the leading constant is dominated by the cost of the oracle for evaluating f. Okay, so we have order 1/2, and this order 1/2, well, it's a consequence of Biennale's formula, or the central limit theorem, if you like. So about the order 1/2, typically we cannot do much at first. But a question we can think of is, can we improve the constant in the error bound? That is, can we improve the variance here, which means can we make it smaller? And well, let's try. So let's stick at a one-dimensional example here. So now d is equal to 1, and let's try hit or miss Monte Carlo. So there are many versions of Monte Carlo methods for integration. And hit or miss Monte Carlo, well, has an intuitive construction. So let's move to the picture first. So what we are doing, so here's the graph of our function. So it's defined on 0, 1, and in this case also the function takes only values in 0, 1. Well, and then we let points remain uniformly distributed. If we are under the blue curve, well, then we count it. If not, we don't count it. And then the number of points which are under the blue curve divided by all the numbers we have simulated, that's the approximation of the integral. So think again about the estimating of pi in the first lecture. Okay, what does this mean mathematically? So x and y are IID random variables which are uniformly distributed on 0, 1. And for this example here, I already said, okay, f has to be in 0, 1. The values of f have to be in 0, 1. And for all the calculations which follow, we will also assume that f is piecewise continuous. Okay, taking the points under the curve and rejecting the points above the curve, above the graph, well, mathematically this is this. It's just the indicator function of the when that y is less or equal than f of x. So we have values 0 and 1, so that is a Bernoulli random variable. And what is the success probability? Well, the success probability is the probability that z is equal to 1. Z is equal to 1 by definition if y is less or equal than f of x. So we need to compute this probability. And as always, what do? Well, we have two random variables which are independent and have a density, so we use the product of the densities. So we are integrating now over the densities, so density of x, density of y, and over which area we integrate? Well, over the area that y is less or equal than f of x. This is just this condition here. Okay, let's first integrate with respect to y, because then everything gets simpler. So let's exchange the order of integration, which we can trivially do here because everything is positive. That's the version of Fubini, which is called Tonelli. So we need to integrate from 0 to f of x with respect to y, and from 0 to 1 with respect to x. But here, if we integrate from 0 to f of x with respect to y over the constant 1, we just get f of x. So to summarize, the success probability is just, well, the value we wanted to compute. So the integral from 0 to 1 f of x dx. So that's why hit or miss Monte Carlo works. That's why the hit or miss Monte Carlo method works. So the expectation of z of k is the quantity we want to compute, namely s of f. And then we are doing just the same as in classical Monte Carlo. We take n copies, n IID copies of z of k, and we average everything. And for this n IID copies of zk, we need IID copies of xk and yk. And because zk has the right expectation, our method is bias-free. And so, well, the mean squared error is just the variance. So this is again 0 and can be dropped. And what is the variance of M of f? Well, that's the variance of one Bernoulli random variable with success probability p, and this is p times 1 minus p, and as always we have to divide by n. So again we have 1 over n for the decay in n, and here we have the variance. And the question is now whether this variance here is better than the variance of classical Monte Carlo. But not only the variance, so here's a summary, so we just plug in S of f for p. Looking only at the variance will be dangerous. Why it will be dangerous? Because we always have to think about the cost. Well, if you have something with a really low variance but a really, really high cost, well, then the high cost can make all the effort useless, because the high cost can outweigh the low variance. And what is the cost in this case of hit or miss Monte Carlo? Well, so again, we have n evaluations of our function f, so we need to call the oracle n times, so we have n times c. Then we need the xk and yk n times, so we have 2n random numbers, so that's the factor 2n here. Then we have to do comparisons n times, so we have to look whether yk is less or equal than f of xk, and we have 0, 1 assignments. So this gives us a cost of n. That's the blue one. And well, for summing and dividing, we have n minus 1 additions and 1 division. So this is now the cost. So it's n times c plus 4. And the question now is whether hit or miss Monte Carlo is better than naive Monte Carlo. And if you look at the cost, so that's the classical Monte Carlo method, where we just take our IID 0, 1 uniformly distributed random variables and plug it into f and average. That's classical Monte Carlo. Then the cost we have already computed. That's n times c plus 2. And let's go a bit back. Here we have n times c plus 4. So the cost of hit or miss Monte Carlo is higher. And what about the mean squared error? Well, this is the mean squared error of hit or miss Monte Carlo. And this is the mean squared error of standard Monte Carlo. So we now need to compare the variances. And well, for the variance, we have really the same problem. And well, let's look at this small computation here. So if we look at the mean squared error of hit or miss Monte Carlo, which is here abbreviated as HOM multiplied by n, well, then we have the variance of 1 ZK. And for hit or miss Monte Carlo, it's the integral of f of x over 0, 1 minus the squared integral of f of x over 0, 1. That's just p times 1 minus p, which comes from the Bernoulli variable. If we look at the standard estimator and look at the mean squared error, take it times n, well, then they have the variance of f of z1. And what is the variance of f of z1? Well, that's the integral from 0 to 1, f of x squared dx, minus the integral over f of x from 0 to 1 and this squared. So if we look at this line and at this expression, what is the same is, well, the term we subtract. So we only need to compare this term and this term, but f of x is in 0, 1, so f of x squared is less or equal than f of x. So this is larger than this, so not only the cost of hit or miss Monte Carlo is higher than the cost of classical Monte Carlo, but also the variance. So classical Monte Carlo is better than hit or miss Monte Carlo, well, in our computing model. So let's look at a particular example. So f of x is the square root of 1 minus x squared. And in this case, the value of the integral, so s of f, is just pi over 4. And if we look at the variances of the random variables we are using, so for hit or miss or for standard Monte Carlo, so you just can compute here the expressions. And for hit or miss Monte Carlo, you get pi over 4 times 1 minus pi over 4, which is approximately 0.16855. And if you do it for the standard approach, you get just 2 over 3 minus pi squared divided by 16. And this is 0.04982 approximately. So here we have a factor of 3. So classical Monte Carlo is in general really better than hit or miss Monte Carlo. But clearly there are other variance reduction methods. So hit or miss Monte Carlo, well, why I showed it to you? Well, it's a method which has a nice geometric interpretation. It can be useful in some situations, in some really particular situations, particular where f might be really expensive to evaluate, but the comparison y less or equal f of x might be cheap. So that's why I wrote here in our computing model. But the main reason why I showed it to you is that always in numerics. So some people show to you a new algorithm, claim that it's really great, but it might not be great if you do a thorough analysis. There's always a caveat about new methods, you have to analyze them. Well, okay, so here's a list of the so-called variance reduction methods. And as a reference, here's the classical Monte Carlo method, which we have seen quite often now. And the first method is the so-called method of antistatic variables. What we are doing here, so we do not use only f of zi, but also f of 1 minus zi. Why we can do this? Well, if z1 or zi is IID uniformly distributed on 0, 1D, then also 1 minus zi. So this object here and this object here have the same distribution. Well, they are not independent, but the lack of independence is a feature which makes the method of antistatic variables possibly useful. You can see this in the exercise on the new sheet. So we have f of zi, f of 1 minus zi, we sum it, then we are summing over the i's, and we are again averaging over n. And well, we average not from 1 to n, but only to n half, or more precisely the integer part of n half. Because, well, the number of the evaluations of f is the quantity which counts. And also, if we would sum here from 1 to n, we would have to here to standardize by 1 over 2n. Well, that's antistatic variables use not only zi, but also 1 minus zi. A control variates is another method. And control variates, there in the integration problem, we split a part of the function which we want to integrate, and we are splitting a part which we can integrate exactly. So here we are splitting a g, well, from 0, 1d to r, where we know the integral explicitly. So we already know this. And then we are doing classical Monte Carlo, but not classical Monte Carlo on f directly, but now on the difference of f minus g. And the idea is, so if f minus g is small, then the variance of this method might be smaller than the variance of classical Monte Carlo. Okay, so the next variance reduction method is stratification. And here I will restrict for simplicity to d equal to 1. And the same as for important sampling, which is also presented here for d equal to 1. So all the variance reduction methods have an idea behind them. And if you look at stratification here, it looks rather difficult. And do not wonder, so here this factor xj minus xj minus 1, it will disappear soon. So I redacted redacted the slides afterwards because I discovered a typo. And I'm doing the stratification part again now. So what are we having here? So the easiest way to understand stratification is, well, that we are cutting down the interval from 0 to 1 in smaller parts, namely in the subintervals from xj minus 1 to xj. When j runs from 1 to k, so we have this k subintervals. And on each of these subintervals, we are now doing standard Monte Carlo. That's here, the expression inside of the first sum is for each subinterval the standard Monte Carlo estimator. Because now we have the integral from xj minus 1 to xj, and we are using still IID random variables which are uniformly on 0, 1, we have to modify the integrand a bit by this change of variables, which gives this correction factor here. So that's the basic way to understand stratification, splitting up the big integral into smaller parts and doing classical Monte Carlo estimators for the smaller parts. Okay, so now the last method, which is the so-called important sampling method. Well, this method is the, I would say, least intuitive method, but can have a quite good variance reduction. So this is our important sampling estimator. So we still want to integrate f. And here we are doing, well, the classical averaging principle, but not of f of zi, but of f applied to the inverse of capital H applied to zi divided by small h applied to the inverse of capital H applied to zi. And the small h here is a function from 0, 1 to 0, infinity, 0 excluded, so it's strictly positive. And the integral over small h is just 1, and capital H is the antiderivative. So having this here, so strictly positivity, and integral equal to 1, then small h is in fact a density function, and capital H is the corresponding distribution function. So, well, why this is a good method? Well, so let's rephrase it a bit first. So here, as a reminder, so h is a strictly positive density function with distribution function capital H. And then, well, if capital H is a distribution function, then the inverse of h applied to zi is in fact the ITM method for sampling from a random variable with density small h. So in fact, our important sampling estimator is doing this. So we are sampling f of xi divided by h of xi, small f h of xi, IID copies, and then averaged again. And well, this method here is still a good method. Why? Well, if you look at the expectation of this random variable here, by a direct computation, you see that the expectation of this is still the integral from 0, 1 f of x df, the quantity which we want to estimate. So here we have now xi or x1 up to xn IID with density h. So we are losing this this framework here that's z1 up to zn are IID copies of uniformly distributed, uniformly on 0, 1 d-distributed random variables. That's not a problem. We can rewrite this in this way with the ITM method, but the analysis is better done in this general framework. This general framework of a general quadrature problem, as here. So that's why we will do the analysis of all the methods I showed to you in a more general framework in the next chapter, which means after the Easter break. And before the Easter break, I would like to show you a simple application of the stuff which we did, namely a waiting queue example. And as you will see, we don't need much for this small problem. Okay, so queuing systems are a major application of Monte Carlo simulations. And here's a toy example. So we have a queuing system with n service lines. This might be telephone lines or counters. Think about the airport check-in. Well, it might not be a good example today, but you might think of them. VPN access points. So we have n service lines. The customer queries, or the customers, arise at random times. And the procedure is now as follows. So each customer query emerges first at line 1. And if line 1 is available at time ak of the arrival of the case query, so ak are the arrival times, well, and if this line is available, then this line takes care of the query and is a certain time occupied, and this time is tbes. So if line 1 is available at time ak, then this line takes care of the query and is occupied for this amount of time. Well, if line 1 is occupied at time ak, then the query is immediately moved on to channel 2, or channel or line 2, etc. And if the nth line, so if all the lines are occupied, so we start with 1, if 1 is occupied, we are going to 2 immediately, instantaneously, then we are going to 3 if 2 is occupied, etc. If all the lines are occupied, which means if the nth line is also occupied, then the query is rejected. So then you are kicked out, so there's no annoying waiting loop. And the question is now how many queries are accepted, rejected on average. And that's important for the company to know, which has this queuing system here. So you don't want to deal with all of them immediately, because that would be too expensive, but you cannot reject too many. Okay, and how do we model this? So here we have a basic model, so that the queries emerge at times ak, and we are proceeding from 1 to n, and if all are occupied, then we are rejected. But for simulating the system, we need a bit more of modeling input. And the first thing is we need to model is the arrival of the queries. Well, on the previous slides, there was just randomness stated. And the typical model for the arrival of the queries is to model the inter-arrival times, capital T1 up to capital T2, as exponentially distributed with parameter lambda greater than 0, and also, of course, independent. And exponentially distributed inter-arrival times, well, that's a really standard model. In particular, because the exponential distribution has the property of no memory. So tk are the inter-arrival times. So for the arrival times, we have a1 is equal to 0, and then ak plus 1 is tk plus ak. That's the arrival of the queries now. That's the model for it. Well, and how do we model the availability of the lines? So this can be done easily by just having these variables vi of t. And vi of t is 1 if line 1 is available and 0 else. What we also need to do is to fix the simulation horizon. Well, this is from 0 to capital T. That's simple. And also for the modeling, well, we need to have this rejection line, and the rejection line is always available. So Vn plus 1 of t is always 1. Okay, and if with this basic modeling, we can directly write a program. So here's the pseudocode or the simulation scheme. So we start at 0. At the beginning, all the lines are available. So vi of 0 is equal to 1 for all i's from 1 to n plus 1. And the number of accepted jobs and the number of rejected jobs, jobs means queries, is 0. Okay, and then while our running time is still less than the simulation horizon, we are sampling the next inter-arrival time, so capital TK, and increase the time. And well, that's the next customer or query which arrives. And having this arrival of the customer or the query, we then need to find the minimal n where we have an open line. So we need to find the minimal I with vi of t equal to 1. Well, if a real line is open, so if this I is from 1 to n, well, then we make this line occupied by setting vi of tor equal to 0 for tor running now between t and t plus the working time which is needed. So then this is the I we found. We make this line occupied, so the customer wish is accepted, and so we increase the number of accepted customer wishes or queries by 1. Well, if this I is not between 0 and n, well, then the rejection line was the only open line, and we increase the number of rejected queries by 1. And that's it. So we have here this while, which we end with end while. We have this if, which we're ending with end if. And here, well, here are the inter-arrival times. And for each arrival of a customer of a query, we are looking whether we have an open line. If yes, we are fulfilling this wish and make this line occupied for t best minutes. And if else, we reject. And to take count, so we have now this number of overall customers which arrived, which is, oh, here's a typo, it must be C and T only. So this mu f and mu up, so the number of accepted and rejected customer queries is the overall number of the queries. And the relative number we are getting by standardizing mu f and mu up by count in each setting. So then we are getting the average number of accepted customer queries and rejected customer queries. Okay. So, and here's a small simulation study for it. So here we have lambda equal to 1 for the inter-arrival times. Here's the working time needed, and n and capital T are varied here throughout the example. So n was the number of lines we had, and t is the simulation horizon. And here's lambda equal to 1, t best is equal to 2, and n and t is variable. And here we have lambda equal to 1, n is fixed, and here is the working time, and the simulation horizon is variable. Okay, what we can see from the simulations. So first of all, for fixed n and all the other parameters fixed, there's a stabilization effect for t increasing. So here you can see we have 0.5204, 0.5, 1.54, and here you see it seems to stabilize around 1/2. And the same effect we have with the other parameter sets. Also here, but of course it stabilizes to different values. Okay, what we see here is the convergence of a stochastic process to its stationary distribution, and also there's an ergodic theorem of work. If you had this introduction into Markov processes lectures from live, well, then you know what the stationary distribution is, a stationary distribution of a Markov chain, and something similar is going on here. So we have this stabilizing effect for t increasing, which means that the system approaches the stationary state or its steady state. Okay, what else do we see? Well, for n equal to 1, 2, and 3, so that's the number of lines. If we have 3 lines in this setting here, well, typically all jobs are accepted. Well, a company could do this, but it would say, let's try to save some money and move down to 2 lines. And with 2 lines in the setup, still many jobs are accepted. So this is economically that might be better. If you increase, or if the company decreases the number of counters further, well, then we have only 50%. 50% is not really good for customer satisfaction. Okay, That's one thing you can read on this table. And in the second table, well, the working time is increased. And here you have a similar effect. Well, as I said, they're stabilizing. And if the working time is 2, and we have 2 lines, well, then there's a stabilization close to 1. If we have 2 lines and the working time is increased to 3, then basically 2 over 3, 2 out of 3 customers are accepted in average, and if we are moving the working time up to 4, then we again have only 50%. So this is a small simulation study, and well, queuing system is a really, really big application of Monte Carlo systems. So queuing systems or discrete event systems. But as I said, I wanted to show you a small toy example before the Easter break, some application, and if you have fun to do this, well, to reprogram this on the new exercise sheet, this is exercise 4, just to do the reprogramming. But it's not really difficult because all the pseudocode is already written here. Okay, that's all for lecture 8. So we will continue after the Easter break. In which form is unclear now, but we will definitely will continue. Well, and enjoy your Easter break. Well, it sounds a bit funny, but just stay healthy. And I hope to see you again soon in person.